Welcome everyone to the second session of the course, Statistical Learning in Practice. Today, what we're going to do is to hopefully finish up GLMs. So I will go a bit fast in this lecture because, as I said, it's not formally a prerequisite, but what we're seeing is sort of very well established results. And if you have not seen any of this, then I again suggest that you take a look at the statistical modeling notes that I have on my website, where you don't need to understand the proofs, but at least be familiar with the usual results for this topic. Okay, so we defined in the last lecture EDFs, so exponential dispersion families. And let me give you, a few properties, and then we'll go into the GLM. So for you to check is the following. So check that if a random variable z follows its distribution is from an exponential dispersion family with parameters theta and phi, then the expectation is given by this, so the derivative of a k evaluated at the parameter theta, and then the variance of z is phi times this k differentiated twice at the theta parameter. Okay, so to check this, you may use, for instance, the cumulant generating function. And it shouldn't be too hard. Okay. So given this, and let me call this star, the variance expression. So by star together with the non-degeneracy, so this is not something you need to check. This is already something I'm telling you. So the non-degeneracy of the distribution, we have that k prime is actually invertible. Okay, let me close the email. So it's invertible. So this means that we can parameterize or reparameterize this space of distributions or set of distributions with respect to the mean parameter, okay, which is the following. The mean parameter, which is this mu, which is going to depend on the theta parameter and is defined as precisely this derivative, right? Because that's the mean, as we said. And this parameter lives in a space that we call the mean space, mean parameter space, and is given by calligraphic M, which is just the images of the thetas through the mu function, right? So the thetas belong into the parameter space. So the natural parameter space, basically. Okay, so with some abuse of notation, we're going to write theta not only for the natural parameter, but also for the inverse function, okay, of this mean parameter. So this is therefore just the k prime inverse evaluated at a mu, okay? And given this, we can write the variance expression that we had above simply as, it was the second derivative of theta, second derivative of k evaluated at theta, and so we can just evaluate it at the function of the mu, and this is going to give us phi v of mu. Okay, so we define the v through this, where we call the v the the variance function. Okay, so it's a function of the mu in this case. Okay, so 3 examples of EDFs, and I'm going to let you check that what I claim makes sense. So first example, we can take what you expect, which is the normal distribution. So we started sort of motivating GLMs as a generalization somehow, or maybe just as a set of distributions that includes the normal distribution. So then, of course, we should check that. This is the first example that we can think of to check the different properties or the parameters of this family of distributions. So I claim that this is indeed an EDF, an exponential dispersion family. And in this case, this EDF has the following parameters. So it has theta equal to gamma, gamma being the mean. Then the dispersion parameter is the variance parameter. Then the k is theta squared over 2. And so we can differentiate this to get that mu is theta, which, by the way, of course, is equal to gamma, as it should be, right? And the v, so the variance function, if you differentiate this again with respect to theta, then you get that this is 1. And just as a sanity check, of course, the phi, and the v, when we multiply them together, it should be giving us the variance. So that's, of course, sigma squared. And then again, the mean is the mean of the normal distribution. But do check that these are the parameters arising from this model. Okay, so you have to write the PDF of a normal distribution in such a way that it satisfies the definition of the EDF, and then try to identify each of the parameters from that expression, right? Okay, so second example, we take a Poisson family of Poisson distributions, so lambda greater than 0, and I claim again that this is an EDF with the following parameters. So we have that theta is going to be the logarithm of lambda, then phi is going to be 1, the k function is going to equal e to the theta, then the mu is the derivative, so therefore it's just itself, so it's again the same quantity. And this, by the way, if we substitute the value for theta, then we get this is lambda, and lambda, of course, is the mean of a Poisson distribution or random variable, and so it makes sense so far. And then the v is going to be it's going to be mu itself, right? Because it's e to the theta again. And again, if you multiply the v times the dispersion parameter, then you get mu, and mu is equal to lambda by the previous calculation. And so, this makes sense with the Poisson distribution, right? Okay, and then the last example, and these are really the main 3 families of exponential dispersion distributions. So this is the binomial distribution, but we need to rescale it by its one of its parameters, so by the m in here. So the m is this number of experiments, sort of Bernoulli experiments, and p is between 0 and 1. So again, oh Lord, I'm sorry, is an EDF with the following. Okay, right, that's not good. Okay, good. Okay, so this is an EDF. With the first parameter being, so the natural parameter being the logit function of p. And so if you haven't seen this function, this is simply the logarithm p over 1 minus p. And then we have as dispersion parameter 1 over m, and as k we have the logarithm of e to the theta plus 1, and as mu you can differentiate and get that you get this x-bit function, and this is e to the theta 1 plus e to the theta. So this is the inverse of the logit function, and this is, by the way, called the logistic function. As what gives the name to this model as being the logistic model or logistic regression model. We'll see once we introduce GLMs. And this, by the way, if you substitute the value of theta, then you should get that this is equal to p. Again, that should be that should be making sense, because you would think, well, the mean of a binomial is actually m times p, but because we rescaled by 1 over m, then it should be p, right? And then as variance, we get variance function, we get mu 1 minus mu. Okay, and this again is sensible because mu is p. Okay, so that's for you to check that the three make sense. Let me now then move on into GLMs, right? So far, we've only been talking about, Richard, just in a sec. So we've basically introduced, the probability models that we're going to be using, and then now we're going to really be introducing a model that, we can input some data into it, and then it becomes a statistical model. So there is a question from Richard Mulange.
Hello. Just to check, back in the definition from last lecture, we talked about having the density f with respect to some sort of dominating measure. I think you said not to worry about the details too much, but I was thinking, for examples 2 and 3, what would be the measure you'd need for Poisson and binomial?
So that's a good question. So these are, basically you can have the counting measure, for instance. So the counting measure is just a measure that has basically Dirac deltas at each of the natural numbers. So of course, in the binomial with the rescaled version, you would need to sort of play around a bit with that. But in the Poisson, which is the one that is easier to understand, you can have the counting measure on the natural numbers, which what it does is basically to assign some measure that could be 1, for instance, to each of the natural numbers. And remember that this dominating measure doesn't need to be finite. It's enough with being sigma finite. So then that's good enough.
Oh, thank you.
Right, no problem. Okay, so let's then move into GLMs. So 1, 1, 2, and that's generally the case. We'll be thinking of models that are either continuous with respect to Lebesgue or with respect to the counting measure. Basically, that's yeah. Okay, so the generalized linear model. There's GLM, or generalized linear models. Okay. So let K be, K and this set of distributions, which is now, so now I'm going to write them parameterized by the mean parameter rather than the natural parameter. So let this with mu in the mean parameter space and phi in its parameter space. So let these guys be as above. Okay. Then we define, so definition 2, the GLM assumes that yi, which are, is one of the observations, these guys are going to follow a an exponential dispersion family with parameters mu I, phi I, and this is of course for all observations, and note that they have different mu and phi parameters, but they do belong to the same sort of P family. Okay, so we're not assuming that the y's, for different i's, the y i's, arise from a normal and then also a Poisson and so on. We fix, the family, so we fix a Poisson, and then is the parameters of the Poisson that are going to be changing for each of the observations. And then really important as well is the independence between the observations. Okay, so of course they cannot be identically distributed because the mu i's and the phi i's are different for each observation, but it is important that we assume independence. Yeah. So we assume this and such that, so let's specify the mu i's and the phi i's. So for the mu i's, what we're going to have is that the image of this mu i's through some function g that I will talk about in a sec equals the xi transpose times beta, which, by the way, I think I may have said that it was a linear regressor, but it's a linear predictor, excuse me. So I will sort of make a little note about that typo in the notes. So I just remembered. So beta being in our P, and this is unknown, so just like in the normal linear model. And then G, which is a function from the mean parameter to the real numbers, is what is called the link function. Okay, this is the link function. So it links the linear predictor to the mean of the model. Okay, so linear function, and this is known. I mean, it's not only known, but we choose it. Yeah. Okay, and then the second, so now we need to talk about the phi i's. So the phi i's, we assume that they have the following form, and is that they are the product of some a1 and an greater than 0 that are called the weights. Sorry, I'm now writing lowercase. What the heck? Okay, fine. Okay, so weights, and these are known. So again, we can choose these, although actually we may not choose them. They may be given by the distribution, but anyway, they are known. And then phi greater than 0 is the dispersion parameter. Okay. So you'll be thinking, okay, so then we have, two definitions of dispersion parameters. So not quite, just because, so this is possibly unknown, by the way. So this is something we sort of spoke about in the last lecture, that it depends on the distribution, whether this is going to be unknown or not. Yeah? So yeah, just a comment about the name of dispersion parameter. I mean, dispersion parameter had a definition in an EDF before, but then we're in a GLM now, so we call the phi the dispersion parameter rather than the product of the AIs and phi's, although you may just call that dispersion as long as it's clear by the context what you're talking about, right? Okay, so let's make a couple of remarks. Do interrupt if you have any questions, or sort of raise your hand as Richard did. So remarks. So some assumptions that we'll be silently assuming are the following. So unless otherwise stated, we assume that P is always less or equal than n. X, the design matrix, is full rank. And G, the link function, is strictly monotonic. Generally, I think we'll only see increasing, and twice differentiable. Okay. And then second remark, commonly we take G of mu to be equal to the theta of mu function, okay? And this is what is called the canonical link. Okay, and then in other occasions, or just actually, it happens that the canonical link, so in some occasions, we may not take the canonical link, but we take G such that the image of a mean space is the whole of the real line, or it may be that actually the canonical link, generally speaking, satisfies this straight away. So that's what I mean by or and. And so this means essentially what we have here is just that the G function is surjective, yeah, and that should be sort of intuitive why we wish to have that. And this is because if we remember that the image of the mu i's is going to be the linear predictor, then we don't really want to have issues with the values that the predictor can take, so that then you don't have a counter image or any of this. Yeah. So so we have surjectivity, and with the strict monotonicity, essentially we have bijection, which is something we wish to have, because we wish to have a different mean parameter for each value of the beta and the other way around, right? So we wish to have some sort of identifiability, yeah, of the beta. And the twice differentiability of the G function is really generally assumed just for so that the computations make sense and we can differentiate things enough. And actually, the relevant GLMs, generally, they always satisfy this if we take the canonical link. Okay, and then maybe let me say, so third, that the canonical link for the normal linear model, the Poisson model, and the binomial model is the identity function, the logarithm, let's say logarithmic, and logit function, or R, maybe that's grammatically a bit better. So they are canonical links for these guys are the identity logarithmic and logic functions respectively. Yeah. Okay, so that is just immediate from the calculations that we did before, right? Okay. Okay, so we have now the definition of a statistical model that we want to be using. And so the next question is, how do we estimate the parameters, right? Okay, so estimation, so 113. And then it's estimation of beta, and then, possibly a phi if it is unknown. So let's assume that y, which we define to be just a vector of y's, of targets. So this guy follows a GLM. Then the log likelihood function is given by the following. So we write the little l as usual of beta and phi, which is of course a function of the data as well. So therefore it's a random function. But generally we omit that because we're interested in the in the functional relationship with respect to the unknown parameters. And so this is given by the sum from 1 to n of this you can check, it's simple to check. So it's given by this sum So here we wish to then write the theta parameter, right, times the yi, but the theta parameter is not good enough because we wish to have the dependence on the beta. So how do we get that? Well, we need to write the theta in terms of the mu, and then the mu in terms of the beta. So we can directly invert the g function and get this quantity here, yi minus k. Now the k function exactly at the same sort of value. I'm sorry, it's not going to fit. I think it's clear. Okay, and then I left out the h function. So this is now the logarithm of the h function at each of the y's and at ai phi, right? Okay, so that's the log likelihood function, and we're therefore, ready to say something about at least the MLE for the beta. So let me begin with the beta as a proposition. This is proposition 1. So let, as we were saying, so let y follow a GLM, satisfying the usual regularity assumptions for consistency of MLEs. And with the canonical link, okay? So if you haven't, so for those that did undergraduate, the undergraduate at Cambridge, they will have, well, you'll probably have taken the Principles of Statistics course, which, at some stage it included these regularity assumptions. You don't need to know them for this course, but just be aware that there are some assumptions that guarantee that if you have an MLE, so by the way, I remind you that the MLE is the maximizer of the log likelihood, which is the maximum likelihood estimator. And consistency means that it will, as you get more and more data, this estimator will converge to the value that is underlying the, the probability distribution giving rise to the data. And so assuming this, what one gets is existence, not necessarily uniqueness, but existence of MLEs, and then consistency, of course, as I was saying. And so what we're going to assume is that we have such regularity assumptions so that the MLE exists. And then we're also assuming that the, specifically for the GLM, that we have the canonical link. And so if we have these two things, then the MLE exists and is unique, actually. So the canonical link will give us the uniqueness. And it's unique. And writing mu I hat equal to the mu function evaluated at the linear predictor, but now at the MLE beta hat. Yeah, maybe I should have said the MLE beta hat. Okay, the beta hat. This guy is going to solve, the MLE solves the so-called score equations. And these are given by the sum from I equal 1 to n of xi over ai times yi minus mu I hat being equal to 0. Okay, so remember that the xi is a vector of p components, and so therefore we have p equations embedded in this expression, right? Okay, so I will, let me see, so we have maybe not so long left. Okay, so I will okay, I will give the definition then. Well, okay, fine. I will prove this now. Then worst case scenario, we can use just a bit of time in the next lecture for finishing the section. Okay, to prove, and the canonical link, and this is probably one of the few proofs that we're going to have, and it's not really because it's a difficult proof, anything like this, but it's just that we get a bit used to doing the calculations with the GLMs. So under the canonical link, we have that the log likelihood, at least in terms of the beta, is going to be a constant plus the sum from y equal n, and we have this expression here. And now remember, we had the theta at g minus 1, but g is theta, so g minus 1 is theta minus 1. So then we just get a cancellation, and we get directly this value, yi. And this is, of course, going to simplify things a lot. And this is why, the canonical link is the usual choice of the link function. So, okay, so we get this, and now differentiating with respect to beta, we get, so firstly the gradient, we get, this is the sum from 1 to n of the xi over ai phi times yi minus k prime xi transpose. So you can check that these things make sense. That's xi. And then the Hessian is given by this expression I'm going to write. So this is negative of the sum of xi transpose ai phi, and then the second derivative. Okay, and then since we have that the second derivative is positive, okay, at every element, and this is because it equals the variance, and the variance is going to be strictly larger than 0 because we have the non-degeneracy for every element in the family of distributions. So this, together with x having full rank, gives that the Hessian is negative definite. And therefore, L is strictly concave, which means that, well, let's say, so this is what I was saying in words as we were writing the proposition. So this, together with the regularity assumptions, gives existence and uniqueness of the MLE, and then just setting the gradient to 0 gives the score equations, right? Okay, so that shows the result. And okay, so we have now a recipe to get the beta, which is to try to solve, or the estimator for beta, which is to try to solve these equations at the top of the page, right? Okay, so if we have to solve or find the 0 of a function or of an equation in this case, then we have that methods to approximate beta hat are so one famous one is Newton-Raphson, for instance, and variations. And then also the Fisher, more particular to this, is the Fisher scoring. Sorry, not more particular, so this is just a method, but what is more particular is that this name, this methodology within GLMs is also called iteratively reweighted least squares. Also written as IRLS. Okay. So we'll see this in the practicals. Okay. Okay, so that's regarding beta. What about phi? Well, if phi is unknown, then it's so it's MLE or MLEs, right? Doesn't necessarily enjoy such a nice characterization, enjoy similar characterization. Properties. Okay, so then instead we may take a simpler estimator, so a simple estimator motivated from the variance expression that we had. So this is the variance from var of z being equal to phi v, well, phi, sorry, we're in the GLM, so we need the AIs. So AI v mu I is the so-called generalized Pearson statistic. Okay, and this is given by, so we can write just the phi hat. This is 1 over n minus p, the sum from 1 to n of the yi minus mu I hat squared divided by ai, and then the v, which is known, at the mu I hat. Okay, and by the way, if phi is known, then we're going to set phi hat to be phi, but I just wish to carry on with phi hat just for economy of the notation. Okay. Okay, so note that this phi hat is actually a generalization of the estimator of the variance in the normal linear model. Okay. So if we specify, so if we I guess just try to specify the v and the mu for the normal linear model, then you will recover the usual estimator of the variance. Okay. Okay. So then now that we have estimators, let's have some guarantees for these estimators. So how do we construct inferential procedures from these guys? Well, okay. So let's say 1, 1, 1, 4. And this is asymptotic properties or guarantees. Okay, so and you should be familiar with the normal linear model. you remember that the residual sum of squares played a really crucial role in anything that had to do with inference, right? So we were trying to remember just to construct the MLE, or actually the ordinary least square solution. One tries to minimize, the sum of the squares of the errors that we're making, of the residuals, and then with that one has all kind of results. So now the question is, what do we take as a generalization, or what do we use instead in a GLM in general? So we're going to have what is called the deviance. Okay, so the generalize the residual sum of squares through the so-called deviance. Okay, so let me define this. So what is the deviance? So definition 3. So let L tilde be the log likelihood function, but now parameterized rather than by theta and phi. We're going to parameterize it by mu and phi. Okay. Then the deviance is deviance of a GLM is given by this quantity here. So it's d, generally one writes d, and this is d of y mu hat, and is going to be given by 2 times this dispersion parameter, and then the difference between the L tilde at y. So remember, L tilde now is a function of mu and phi. So in the mu, we're going to substitute the y actually. So for clarity, I'm writing now the dependence on everything, and L tilde, and then here we have the mu hat phi y. Okay, so let me briefly comment on this. So what is this expression? So remark. So if F tilde is the density of the GLM parameterized by again the mu and the phi rather than the sigma and the phi, then we get that the deviance is no more than 2 times phi, and then the logarithm of the maximized density. And now in the density, the dependence, well, the arguments are written in the opposite order. So first the data and then the parameters. And so this is the maximized density when mu can take any value in Rn, okay, over the maximized version of this guy as well, again. But now rather than being unrestricted, the mu, what we have is mu in Rn satisfying that the G mu I equals xi transpose beta. So really what I'm saying here is that we're going to write the mu, each of its coordinates, we're going to write them in terms of the linear predictor, and then we're going to maximize the resulting expression with respect to the beta. Yeah, so that's just the usual density when evaluated at the MLE for the beta in this case. Okay, so why am I saying this? Well, it should be, this expression should be familiar to anyone who's seen statistics before. because this is, so this guy maybe removing the phi dependence. So if we divide it by pi, then this is the likelihood ratio test. Ratio test statistic. For the model at hand. So that would be what appears in the denominator inside the logarithm versus the saturated version. Yeah? So this is again in the statistical modeling notes. And what do I mean by the saturated version? Well, it's just simply that it's the same model. So same model with mu in Rn unrestricted. Okay, so this is very related to the quantity that appears in Wilks' theorem. Okay, so we have 5 minutes. Let's see if we can state the theorems. So Theorem One. So this is, we're going to call this large sample asymptotics, which is the usual asymptotics. So as the sample size grows, and we may shorten this as LSA. Okay, so in a GLM, we're going to assume the following. So we're going to have that 1 over n x transpose wx converges to some sigma as n goes to infinity. So for so W is defined as the inverse of the diagonal matrix given by AI times the V function at the mu I times the derivative of the link function at the mean parameter, and this is squared. And then also we assume that this sigma is non-degenerate, so it's invertible as a matrix. Then as n goes to infinity, we have the following conclusions. So first, we have that the rescaled version of the beta MLE centered at the true parameter converges in distribution to a normal distribution with 0 mean, so therefore it's consistent, but also we have asymptotic normality with the sigma inverse as the limiting variance. And then the second conclusion is that the phi hat will converge almost surely to the phi. Yeah? And then of course, it may be that the phi is known. So remember that I said that if it is known, then phi hat is the is phi itself, and then in that case this is a trivial result. But if it's unknown, then we also get consistency. Okay, and then a third conclusion. So write beta. So let us sort of split beta into some beta naught and beta 1. Where beta naught belongs to some RP naught for some P naught between 1 and P. Then also let omega naught be the model where beta 1 equals 0, and also mu check the MLE for mu. This is under our omega naught. Okay, so then again, as n goes to infinity, and in this case under omega naught, we get the following, and is that 1 over phi hat of the deviance at for this submodel. If we subtract the deviance at the larger model, then this will converge in distribution to a chi-squared on p minus p naught degrees of freedom. Okay, so this is something like Wilks theorem. Yeah, I mean, this is really Wilks theorem. So remember that the deviance, the first term in the deviance, if we view it as a difference of log likelihoods, then it's just the saturated model. So we'll essentially have, the saturated model components will cancel out, and then we have exactly the usual likelihood ratio test statistic, and so we get Wilks theorem, and this follows from that. Yeah, together with the convergence of the pi hat parameter. Okay, so we've basically run out of time, and there is one more theorem that I wish to introduce, but we'll introduce it in the next lecture. So that's basically what is called small dispersion asymptotics, and then we'll be done with GLMs, and we can also have a practical. So again, I'll start with this second theorem the next session, and then we'll go into the practical. So please have R and RStudio ready on your laptops, and I will hopefully upload the first practical tomorrow on my website and on Moodle, and that should be it. If you have any questions, I'm happy to stay for a couple of minutes.